example of a binomial probability distribution. Here's the context of our example. We have a loaded six-sided die. The probability of obtaining a 6 when rolling this die is P equal to 0.4. Consequently, the probability of not rolling a 6 is going to be 1 minus 0.4, or in other words 0.6. Now we're going to call that Q. P, the probability of rolling is 6.4. Q, the probability of not rolling is 6.6. We're making reference to a loaded die here. A loaded die is one that is not fair. A fair die, if you have a fair die, the probability of getting 6 will be 1 out of 6 because you have 6 faces. If the die is fair, then each of them will be likely, equally likely to occur. That doesn't happen here. The probability of getting 6 is not 1/6, but rather something else, 0.4. That is why we're calling this a loaded die. Here's our experiment. Roll our loaded six-sided die a total of 16 times. Let x be the number of 6s obtained. Here x is what we call our random variable. Find the probability that A, exactly 7 6s are obtained. B, at least 2 6s are obtained. Now, let's look at A. What is the question that's being asked in A? If you look at your random variable, you will see that the probability that we want is that of x equaling 7. The probability that exactly 7 6s are obtained. That means since x is the number of 6s obtained, we're looking for a probability that x equals 7. Now, when you think of the outcomes of this experiment, you quickly realize that there are many ways of achieving this type of an outcome. I have 2 here on the board. Maybe the first 7 were 6s and the remaining 9 were not. Or maybe the first one was 6, the second one wasn't, the next 5 after that were, the one after those was not, then this next one was a 6, and the remaining 7 were not. So there are many different outcomes that will satisfy getting 7 6s. Now, this may seem like a very difficult problem to deal with, but let's take a look at these 2 particular outcomes. Let's compute the probability of each of them. Now, you want the probability of getting 6 followed by 6 followed by 6 a total of 7 times. What is that? Well, for the first trial, you get 0.4 because the probability of getting a 6 is 0.4. And same deal for the second trial. You want a 6, then your probability is going to be 0.4. All of this all the way until the 7th one, which is again 0.4. Now, after the 7th one, you want the probability of not getting a 6. What is that? It's 0.6. And the next one, again, it's not a 6, it's 0.6. All the way until the last one. They're all 0.6s. So if you ask, what is the probability of getting the first 7 6s and the last 9 non-6s? The probability is going to be the product of this individual probabilities. 0.4 to the 7th times 0.6 to the 9th, because there are 9 of them. So you have 0.4 to the 7th times 0.6 to the 9th. Now that was just this case. What about this additional case? Well, let's think about what you're going to get for the 6s. 0.4, 0.4 for each of the 6s. So you get 0.4 here, 0.4 there, and so on. You can get 0.4 over here as well. Now, here in between, you're going to get a 0.6, right? 0.6. Because that's not a 6, the probability of not getting a 6, again, is 0.6. And then there, 0.6. And then there, 0.6. Up onto the last one, 0.6. Now, you want to calculate the probability of this outcome, go ahead and multiply these guys out. How many 0.4s are there? 7 of them. So the probability of this outcome is going to be 0.4 to the 7th times 0.6 to the 9th, because there are 9 non-6s. Now, you will realize that no matter how the outcome is configured, the probability of each individual outcome will be 0.4 to the 7th times 0.6 to the 9th. They're all the same. Each individual outcome has the same probability. So our task becomes how many outcomes are there, because we need to add them up. We need to add the probabilities to get the overall probability. Well, let's take a look at what we need to find out. We need the number of ways to position 7 6s in 16 slots. How much is that? Well, that's going to be 16 choose 7. So there are 16 choose 7 possible outcomes that satisfy our condition x equals 7. You want 7 6s. So you're adding this guy, 0.4 to the 7 times 0.6 to the 9th, a total of 16 choose 7 times. That will be your probability of obtaining precisely 7 6s. Now, earlier I did the calculation of this. I did 16 choose 7, gave me 11,440 times 0.4 to the 7th, which is 0.00163 and some change, times 0.6 to the 9th, which is this will be 0.01007 and change. Now, when you perform the calculation all together, you get that the probability of obtaining exactly 7 6s is 0.1888892 and some change. All right, let's look at the second example. Example B. What is the probability that at least 2 6s are obtained? There are several cases to consider. If you want the probability that x is at least 2, that means that you're looking for the probability that x is greater than or equal to 2. Now, there are many possible cases. You could have exactly 2, or you could have exactly 3, all the way up to 16. So there are exclusive alternatives. So we, in theory, could say, okay, the probability that x equals 2 is the same as the probability, the probability that x is greater than or equal to 2 will be the same as the probability that x equals 2, plus the probability that x equals 3, plus all the way up until the probability that x equals 16. Now, when you calculate the individual probabilities, you run into scenarios similar to this right here. You have to compute, for x equals 2, you have to compute the number of ways in which you can get an outcome with exactly 2 6s, and then you have to say 0.4 to the second, because there are 2 6s, and then 0.6 to the 14, because if you have 2 6s, then you have 14 that are not. But then you have to do it for x equals 3, and you have to do it all the way up until x equals 16. So that is a very time-consuming calculation. Now, let's consider the following. What about if I look at the complement of this event? Where is the probability that x is greater than or equal to 2? Well, we have a rule that says the probability of an event is 1 minus the probability of its complement. The complement of x greater than or equal to 2 would have to be the cases where x is not greater than or equal to 2. But what is that? You either get 0 or 1. So 1 minus probability x equals 0 or x equals 1. These are exclusive alternatives, so you can actually break this down as 1 minus probability that x equals 0 minus probability x equals 1. So this calculation right here is not as long as that one. So sometimes you will have a problem like this. You have a problem where you're saying the probability that the random variable x is greater than or equal to a certain fixed number. And when you look at the problem in a direct manner, you find that there are several. There are too many alternatives to consider. Maybe looking at the complement will reduce the number of alternatives. In this case, it did. There you have about 15 alternatives. Here you only have 2 alternatives to consider. So we choose this method of solution. Let's find the probability of our event by looking at 1 minus the probability of its complement. So let's complete this exercise this way. Notice that if you did it that way, you should get a good answer, but it is extremely time consuming, and really it is error prone. You could make a mistake easily. Something could go wrong when you're performing your calculation and you end up getting a bad answer. Here you're never error free. You probably will make a mistake here, but it will be less likely to occur. If you're very careful, you're likely going to get your answer out of this. So it's going to be 1 minus probability x equals 0. Now you want 0 sixes, then that means that all the 16 will be non-sixes. So it's 0.6 to the 16th power because all of them are non-sixes. Minus, now here you want 1/6, so that's 0.4. And you want 15 non-sixes, so that's 0.6 to the 15. Now, how many outcomes are there that have exactly 1/6? Well, let's see. You want to position 1/6 in one of these 16 slots. There are 16 choose one ways of doing that. Now, earlier I did this calculation. I put that in a calculator. I did the calculation very carefully. I ended up finding out that this is the same as 1 minus 0.000282, etc. minus, that took care of this guy. And then the other one was 0.003291, etc. At the end, after you put all this together, you get 0.996708 and change. Okay, this pretty much concludes our 2 examples of binomial distributions.